we need to find, or we need to find a formula for V average, I average, VRMS, IRMS, RMS, etc. So we can say the following. So we need to find V out average. So we will go back to the waveform. This is V out, and it is a full wave rectified signal. Omega t by 2 pi Vmax Vmax. So as you can see, the average should be double the half wave, but we can do the proof. So V out average equal to 1 divided by pi integration from 0 to pi Vmax sine theta d theta. This is the first one. And because it is symmetric, we can divide by 2 pi to take the whole cycle, and we have two waves, so we will multiply it by 2, okay, which is the same. Just take one wave only. So the average here is the same as the average here, okay? So this value equal to Vmax over pi, and the integration of sine theta is cos theta, and you reverse the limits because it should be negative cos. So V out average will be 2 Vmax over pi, and as you can see, this is double the half wave case. To find V out RMS, we will do it, but if you compare the sine wave V of t as AC sine wave, and you compare the full wave rectified V of t, full wave DC, you can see when you square this, it will be this wave squared, and when you square the negative, it will be positive square. So when you square this one, when you square this one, you are getting the same wave, because the squaring will remove the negative. So I'm expecting that the RMS in this situation will be the same as the RMS of the sine wave, which is Vmax over root 2. This is what I'm expecting. But let's do the proof. So how we will do the proof? VRMS is square root for the average 1 over pi integration from 0 to pi Vmax sine theta d theta, which is the expression for the average, but we will square the wave. This will give us Vmax square root 1 over pi, and sine square is half 1 minus cos double the angle, and we are integrating from 0 to pi. So V out RMS will be Vmax square root 1 divided by 2 pi, and this integration will be theta minus sine 2 theta over 2 from 0 to pi. If we put the limits, it will be pi minus sine 2 pi over 2 minus 0 plus sine 2 multiplied by 0 over 2. So this is 0, 0, 0. So this integration will be pi. So you can see that V out RMS will be pi, will cancel pi, will be Vmax divided by root 2, which is the same as an AC sine wave. To get I out average, it's a V out average divided by R equal to 2 Vmax divided by pi R. To get I out RMS, it's a V out RMS divided by R equal to Vmax divided by root 2R. To get P out average, it is V out RMS square divided by R equal to Vmax square divided by 2R. This is the power average. Okay. So we got the peak inverse value, we got the average value, we got the RMS value for the voltage and for the current. Now we will see a very interesting note. This is very important. Now if you have your source here, this is an AC source. At the source you know what is your VRMS and you know your I source, okay? Which means you know I source RMS. And here you have a resistive load, pure resistive load, and here you have your bridge, and this is how we sketch the bridge. So this is a full wave bridge. Full bridge. Okay. So we have a full wave bridge or full bridge. Now if we need to find the power factor seen at the source, so what you are expecting? Don't forget that we have a pure R load here. So how we will find the power factor? So all our assumptions that we have an ideal power electronics, which means the power here equal to the power here. So the power at this point is AC power. So the power here is V source, I source, cos phi. So V source is the RMS of the source, and I source is the RMS of the source current. This is the RMS of the source voltage, equal to, and the power at the DC is V out RMS squared divided by R. Okay. Now what is V out RMS? So V out RMS is V maximum divided by root 2 all squared divided by R. And for the source, Vs is RMS is V maximum divided by root 2. I RMS is V maximum divided by root 2 R. Cos phi equal to V max square divided by 2R. So you can see that cos phi equal 1 or the power factor equal 1. Okay. So we have a unity power factor. Why I source RMS equals this value? So this is I source I RMS. Okay, so it's a sine wave. So the RMS will be the big value divided by root 2. So the big value is V maximum over R. So the RMS will be V maximum divided by R and root 2. So you can see that the power factor in this case is 1. So we can calculate the power factor if we have a power electronics circuit using this concept of making the input power equal to the output power. Okay. Now let's go back to wrap up. So today we continued with RE load. Okay, we didn't cover the effect of the inductance yet, but don't forget the homework, because this is an introduction for the effect of having an inductance. And then we move to single phase full wave rectifier. Hopefully by next lecture we will start we will see the effect of having an inductance. Then we will move to thyristors and controlled rectifiers. So we will finish most of the rectifiers next lecture. Thanks, and see you next lecture. Continue with our power electronics chapter, and we are still in rectifiers, and we studied one electronic switch, which is a diode, and we started by the uncontrolled rectifier. So we studied the single phase half wave rectifier, and we studied the single phase full wave rectifier. We studied the half wave rectifier for R load and for RE load. We studied the full wave rectifier for R load. Today, what we are going to do, we will see what is the effect of having an inductance, and then we will see the single phase full wave rectifier when it has RL load or RLE. After this, we will answer the homework I left to you last time. And after we finish these, we will go to thyristors and we will start our controlled rectifier part. So let's start by the effect of inductance. So effect of inductance. This basic concept is very, very important for this course, and if you are interested in building power electronic circuits, and if you are taking MTE 420, this simple concept is very important. If we have an inductance, and this inductance has a value L, and if you remember, the inductance is a coil around the core which can store flux phi inside the core. The equation we have for an inductance which relates its current to the voltage across it, this equation is V equals L di by dt. And this equation is following a load notation, so I is entering the positive terminal. So if we are sketching the current of the inductor versus time, and the current was increasing, so in this part di by dt will be positive because the current is increasing. So if you take the difference and you divide it by the time, you get a positive value. And when the current starts to decrease, if you find di by dt, it will be negative. But in both cases, the current is still positive. Okay? So in this case, when di by dt is positive, if you look at this equation, the voltage across the inductor will be positive. And in this case, di by dt is negative, so the voltage across the inductor will be negative. So if we sketch the inductor, in this case, the voltage is positive. And if you sketch the inductor here, in this case, the voltage will be negative. So as you can see here, the inductor is charging because the current I is entering the positive, while here I is leaving the positive. So the current I is leaving the positive, so it is discharging. So the inductor can charge or discharge based on the current. If the current is increasing, so the inductor will try to keep the current constant by taking energy from this current. When the current is going down, the inductor will try to support this current by injecting energy back to the system. And this is the operation of the inductor. Now, if we look at L, if this L is small, if the inductance is small, so if the inductance is small, in this case, you cannot store too much energy, which means the inductor current will increase and then it will go to zero fast. Why? Because your time constant, which is tau L over R, so don't forget that the time constant is L over R. Your time constant is small, which means you are discharging so fast. So your current will go to a zero value. So if you sketch I of t versus time, this what will be the shape of the current. So the inductor will try to support the current by injecting energy back, but because this energy is small and it is finite, it will finish in very short duration because we have a small inductor. And we call this case the discontinuous case. So we call this the discontinuous current. So we say we have a discontinuous current. And this is a case you have to avoid in real life. So in real life, we try to avoid having a discontinuous current. Think about this current supplying a motor. If you have a discontinuous current, means you have some time with no current or no torque. Okay, no one would accept this. Now, if we have large L, if the inductance is large, in this case, when the inductor is discharging, it will not reach zero before going to charge again and so on. So this is I of t and this is time. So we are assuming that the energy in the inductor is enough to keep supplying the circuit until you charge again. So you will never go to zero here. And we call this case the continuous case or the continuous current. So we call this continuous current. And the difference between these two peaks, so we call this current I minimum and we call this current I max, and the difference is delta I, and delta I is called current ripples. And you can see in some design requirement or design specification that they put limits on delta I, they put limits on the current ripple, so you are not allowed to exceed this current ripple. Now if L is infinity, so infinite inductance, in this case the inductance will be very high and your time constant will be actually infinity, so the current will never oscillate. Okay, so if we sketch the current I of t, it will be constant. So we call this case where the current inside the inductance is constant. So the inductance is too large and the inductance will keep the current constant. It is has high inertia to change, so the current will be constant. And this is the infinite inductance, or the term we use is highly inductive case. So if the case is highly inductive case, we will have this constant current, which we name it as level current or ripple free current. So these are the cases for the inductance. If you have a small inductance, or if you have a large inductor, or if you have a level or very high inductor. So we will consider our inductor in our solution here for rectifiers that the inductor is highly inductive. And I will tell you what will be the difference between having a highly inductive current or a large inductance, or we have a small inductance. So after we studied what is the effect of the inductance, let's go back to the single phase full wave rectifier in case we have an RL load. So let's go to this case.